Hi, this is an example problem on Young's double slit interference from chapter 27. Pause for a moment to read the question. So with Young's double slit interference, I've kind of drawn a setup here, and here's some notes that we can use to figure out what are the conditions for constructive and for destructive interference. And here's the diagram. We can see that the distance from the slits to the screen is L. The distance between the two slits, the double slit, is little d. And we can look at this central axis and we can measure the distance from that central axis to other points where there may be constructive interference, maxima, bright spots, or minima, dark spots. And at the center, we always have a central maxima bright spot. So looking back at our problem here, we've got a few bits of information that we can write down here. So we know that the screen is placed 1.2 meters from the double slit. So that gives us what our L value is here. Then we know that the distance between the two slits is 0.03 millimeters, sorry. So we've got the distance here between the two slits, D, 0.03 millimeters. And we then have, we're also told now some more information. So we're looking for the second order bright fringe, m equals 2, is measured to be 4.5 centimeters from the center of the screen. So here's the center right here. We call this y equals 0 right here at the center. And as we go up or down from there, we get different distances. So up here we've got y equals 4.5 centimeters. And sometimes I call this this is the bright fringe second order, so I can call this YB2 if we want. And so if we're thinking about the light that's shining here, we're going to try to figure out what the wavelength is. But the idea here is that we've got a central maxima somewhere. And then we're going to have a first order and then a second order bright spot. And let's just check the diagram to see how we label the order numbers, the m's. So we can just go down to the next page here. And we see that for Young's double slit, the central maxima here, this one is m equals 0, and if you go on either side, up or down from there, the next one is m equals 1, m equals 2, etc. So for our picture, we're looking at something like this. Here's the second one. There's your m equals 1, right? Your central maxima here, m equals 0, and m equals 2 right here, the one that we are interested in looking at right now. All right, so it says determine the wavelength of light. This is m equals 2, and it is bright. So it's constructive interference as we saw. Let's see which equation we're going to use for that. We can see that we have a constructive interference, which is bright. D sine theta bright equals m times lambda. D sine, now this is theta bright, and it's m equals 2, equals m times lambda. We're trying to solve for lambda. So we go ahead and divide by m on both sides, cancel our m, and we have an expression for lambda now. The wavelength lambda is going to be equal to d sine theta bright 2 all divided by m. And we know what d is. We know what m is. We don't know what theta bright 2 is. However, there's always a second equation. If we draw a line here straight from the slits, center of the slits out to this one here, you can see that we make a nice little right triangle here. And so we can actually go ahead and use another equation to relate this angle based on that right triangle. So to get the angle from the right triangle, that's going to tell us that tangent theta is equal to opposite, which is your y b2 in this case, right, divided by the adjacent side, which is your L. And to calculate theta now, that's going to be the inverse tangent of these things. And we just need to put those numbers in. So this is 4.5 centimeters. Now I need to get consistent units is important here since they need to cancel. Weeks 0.045 meters divided by L, 1.2 meters. Good, our meters are canceled. That needs to be dimensionless. And when we put that into our calculator, we get an answer equal to 2.15 degrees. And that is the angle theta bright 2. So now we know what this is, and we can go ahead and plug it into the equation for the wavelength. So lambda in this case is now going to be equal to d, which is 0.03 times 10 to the minus third meters. I like to just get it into meters to be consistent. And we have sine of the angle here, which is 2.15 degrees. And then we're going to divide by m, second order, m equals 2. And we'll go ahead and see what our lambda comes out to here. That gives us 5.62 times 10 to the minus 7 meters. Or we can convert that. If we convert it to nanometers, it comes out to 562 nanometers. So that's your answer for part A. That's the wavelength. Now part B says, calculate the distance between the central maxima and the first order dark fringe on the screen. So to understand in the picture where the first order dark fringe is, let's go ahead and look at our notes again to see how the order numbers are labeled for Young's double slit experiment. We see that m equals 0 is the dark fringe on either side of the central maxima. And so we're going to go to the next dark fringe to get to m equals 1. So back to our picture here. We see that for the dark fringes, here's your dark spot, m equals 0. And the next one here, here's your dark spot, m equals 1. And we're going to try to figure out the distance between the central maxima and the first order dark fringe on the screen. So we want to figure out this length right here, from here down to there. It's going to be a new triangle that we make. So if we think about drawing that triangle, it's going to look like this. There. And so we're going to be looking for now this angle here. This was theta bright 2. Now we're looking for theta dark 1. And we need to know theta dark 1 so that we can use the right triangle here to calculate that green distance there, right here. Once we get the theta dark 1, we already know L equals 1/2 meters. We can solve for the distance, that green distance here, which is going to be called Y dark 1. All right. So for part B, to calculate the theta dark 1, we're going to need to use the equation for the condition for destructive interference, which is this one here. D sine theta dark m equals m plus 1/2 theta. So there's our equation, and now we know everything here. You got D, we know what m is, we know what theta is. We just need to go ahead and solve for the angle. So doing a little bit of algebra here, we're going to get sine of theta dark 1. I'm going to divide both sides by d, so I'm going to end up with m plus 1/2 lambda divided by, oops, not 2, d. And let's plug our numbers in. Well, we can go ahead and do one last thing here. Theta dark 1 is going to be the inverse sine of all this stuff. Now we can plug in some numbers here. So m, we know this is m equals 1, first order. We're going to have a 1 plus 1/2 times the wavelength. It's the same wavelength. It's going to be 5.62 times 10 to the minus 7th meters. And then we're going to divide that by the distance between the two slits. So we know what that's equal to. That's 0.03 times 10 to the minus third meters. And so I've gotten my meters consistent so I can cancel them. And now I just need to calculate what this angle is. That comes to 1.61 degrees. And now we can use the geometry of that little that purple triangle there. Now we know the angle. We know the length, the base. We can figure out the height here, the green side there. So using that equation to relate those things, recall that we can write that as y dark 1 is equal to L tangent theta 1. That's just from the geometry of the triangle, right triangle. We'll put in our numbers. So we've got the screen length of 1.2 meters multiplied by tangent of 1.61 degrees. And that y dark 1 comes out to a value of 3.37 times 10 to the minus second meters. Or if we want to write that as centimeters, we can say that that is 3.37 centimeters. Let's just double check here that that makes sense, right? That one, as we can see in the picture, should be lower down than m equals 2, which is at 4.5 centimeters, right? And so this spot right here, a little bit lower down, is at 3.37 centimeters. Yep, that's where it should be. Makes sense. Gives us confidence that we did it correctly. And so here is our answer then for part B.